So that means for your R prime of P, that's equal to negative 8P plus 800. So we need to know where that is equal to 0. So negative 8P plus 800 equals 0. If we subtract 800, divide by negative 8, we know that P is equal to 100. Okay, so that's our critical point. Okay, so that means we have to compare our critical point. Kind of separate that. So we're going to compare R of 100 and our endpoints, which is R of 45 and R of 200, to see which one is actually the highest. Because if they can make more money charging $200 to rent a car, they'll do it. Or if they can make more money charging $45, they'll do that. Or if they can make more money charging $100, they just want to see which one. So this is our critical points. So we kind of separate those. So R of 100 is equal to, where is it? I'll use that one. 800 minus 4 times 100 times 100. So that's equal to 800 minus 400 is 400 times 100 is 40,000. Okay, so now we want to compare it to R of 45, which is 800 minus 4 times 45 times 45. And plugging that into your calculator, you get 27,900. Okay, and if we try R of 200, that's 800 minus 4 times 200. Running out of room. Move that over just a hair. Make sure I have enough room. Okay, so R of 200 equals 800 minus 4 times 200 times 200. And that actually gives you 800 minus 800, which is 0 times 200. So if you charge 200, you actually break even. You get a few people that'll buy it, but not enough to turn a profit. So you have to find that happy medium between charging just enough to make your maximum profit, so it's not too much to where you lose money and people run away, and not too little to where you don't make enough money. So R of 100 is where you make your maximum profit. So when you charge 100, we'll maximize revenue, not profit, revenue. Profit, let me move that up some. Profit and revenue are two different things.
You don't have enough information to figure out the profit.
No. Yeah, we'd have to know cost and maintenance and salaries and all that other stuff.
So what does 800 equal in this equation? I think that's just the price of rental, like, and then minus.
Is the equation?
No, that was the
equation side.
Yep, that was the equation for the number of cars.
Okay, so
Yeah.
it's not even like.
Oh no, it's no specific. Well, it has a meaning, but they just didn't tell us what it is.
Okay.
They gave us the 800 minus 4P.
Yeah.
Right. And 4P is what you consume to be how many cars are there? No, that's.
Yep, that's the price.
Oh, okay.
Yeah. All right. So any questions on that one? All right. here.
How do you know if you've chosen the wrong equation?
You'll get the wrong answer.
I mean, yeah, but you won't know that until.
Really, you want to look at the last sentence or the last line. If they're telling you, like this one, if we kind of go back, you want to maximize the revenue, then your primary equation should involve finding the revenue. If you look on this one, the one before it, they want to know what the dimensions of the fence would be, so we'd have to have a primary equation that measures the length of the fence. So that last equation really
And it's a little
tells
bit
you.
different because they don't want it backs up to the river, so you have one side.
Exactly. Where on this one,
Yeah.
where is it? When you have just a regular ordinary rectangle, you can use the perimeter. But when they give you a rectangle with that missing side,
Yeah.
yep, no perimeter. So there's no one clear-cut way to do it because each question could vary. So I could sit up here and show you 40 examples and you wouldn't see all the ones that appear on the homework. So, oh, this one's a bit rough.
Why I don't like word problems.
That's why I didn't go into engineering. I don't like them.
And unfortunately,
I always tell them, like, if you go into engineering, you have to know word problems. That was not my strong suit, so I was like, bye. I'll leave it to folks who like word problems. Let you make the big bucks. All right. So this is actually a little bit easier. L'Hopital's rule. Okay, so that says we let some function f of x and some function g of x be differentiable. Where we know that the derivative of x, or derivative of g, doesn't equal 0. Okay, so let's say if the limit of f of x over g of x.
you said the derivative of g of x and f of x does not equal 0?
Oh, no, just g of x.
Oh, just g of x. Okay. I saw you just wrote g of x, but I thought I wrote both, so that's why I asked.
Nope, as x approaches some number c. Let's say if it equals 0 over 0. Okay, not our g prime of x, just our regular g of x. Okay. So this is called an indeterminate form. Okay, and you also have indeterminate forms of infinity over infinity, positive infinity over negative infinity, negative over positive, and even if you have negative infinity over negative infinity. Those are also indeterminate forms. Okay, so if you end up with one of those indeterminate forms, and let's say, oh, here, through direct substitution. Okay, so if you end up with one of those indeterminate forms, then you can actually just get the derivative of your numerator and your denominator, and that will give you the same as your limit of just your functions. So let's say, for example, we want to find the limit of 2x squared minus 2 over x plus 1 as x approaches negative 1. Okay. Now, if we use direct substitution, and we just plug in negative 1, we have the limit of 2x squared minus 2 over x plus 1 as x approaches negative 1. We plug it in, we end up getting 0 over 0, which is our indeterminate form. Okay, so as long as we have one of those indeterminate forms, we can apply, and L'Hopital's rule, for the most part, you'll see me use LR instead of writing it over and over and over. So apply L'Hopital's rule. So that means you have the limit as x approaches negative 1. We take the derivative of your numerator over the derivative of your denominator. Okay, and that gives us the limit as x approaches negative 1. That becomes 4x. That 2 disappears, so you just have 4x over derivative of x plus 1 is just 1. Now, if you use direct substitution again, you just end up with negative 4 over 1, or 4 times negative 1 over 1, which is just negative 4. Okay. Now, if you wanted to, you could have divided each term by x, like we did before, and that would have still given you the same thing, but this is just a lot faster. Oh, sure. Let's say if we wanted to, let me see if I have enough room to do that. Let's say we have the limit. So we have our 2x squared. If we divide each one of those terms by x, we have 2x squared over x minus 2 over x divided by x over x plus 1 over x as x approaches negative 1. Here we have your x squared divided by x. So you have the limit as x approaches negative 1 of 2x minus 2 over x over 1 plus 1 over x. Oh, where'd it go? I'm missing something. Oh, where'd it go? 2x squared over x over x over x over x over x. So actually,
That's over x. You're multiplying by, or like dividing by. Because you still got 1
2x squared. Nope, that wouldn't work on this one. That's right. That's why we had to use L'Hopital's. Because for this one, it actually didn't work. It only works when your lead coefficients are equal. There we go. That's right. So you actually couldn't do that for this one. All right. So any questions on this one? All right. Okay, so let's say this one. Next example. I want to find the limit of 3x squared minus 1 over 2x squared plus 1 as x approaches infinity. Okay, so here we have the limit as x approaches infinity, 3x squared minus 1 over 2x squared plus 1. And if x keeps getting bigger and bigger and bigger, your numerator just keeps getting bigger and bigger and bigger. So that becomes infinity. Here, if your x keeps getting bigger and bigger and bigger, your denominator gets bigger and bigger and bigger and bigger and bigger. So you're left with infinity. Okay, which is our indeterminate form. Well, one of our indeterminate forms. Which means we can use L'Hopital's rule.
Question, how many times can you use L'Hopital's rule?
Oh, as many times as you can without that denominator equaling 0.
So you get the second derivative for this one?
Yep, so if you do it and you end up with, just like with this one, we're
Because I
going
was saying it's
to, yep,
gonna
we're going to
happen
end up
again.
with it again.
So you use it.
Yep, you use it a second time.
And that's how you get your answer?
Yep.
Okay, got it.
So you can use it as many times as you can until you can't use it anymore.
It's pretty simple.
Yep, so you have the limit of the derivative of 3x squared minus 1 over the derivative, of 2x squared plus 1 as x approaches infinity. Okay, so that's going to equal the limit as x approaches infinity of 6x over 4x. Okay, and again, if you plug in infinity as x gets bigger and bigger and bigger, your numerator is going to get bigger and bigger and bigger. And as you plug in infinity, your denominator is going to keep getting bigger and bigger. Okay, which gave us another indeterminate form, which means we use L'Hopital's rule again. Yep, so that ends up giving you 6 over 4. So let me write it out. Derivative of 6x over the derivative of 4x as x approaches infinity.
It's not a double derivative, it's just still the normal first derivative.
Yep, just, well, you're technically doing the second derivative, but you just drive the derivatives one at a time. Yep. Okay, so you have the limit of 6 over 4 as x approaches infinity. So the limit of a constant, no matter what it's approaching, is just a constant. So that's 6 over 4, which is 3 over 2. All right, any questions on that one? Yes.
So because it was as x approaches infinity,
Mm-hmm.
we kept going, but like for instance, if it was x approaches like the previous one, -1 or.
Oh, it can be x
1,
approaches anything.
But you want to put you want to just at first derivative just do the substitution rule.
Oh yeah, because if you remember on this one, it was x approaching -1.
Right.
So we just happen to end up getting 0 over 0.
Right.
So you can get 0 over 0, infinity
No,
over
that's what I was
infinity.
getting at.
Mhm.
Was if it was an infinity
Mhm.
and it was -1 or some number,
Mm-hmm.
after the first derivative, we would just plug it in. Correct.
Yep. After you apply L'Hopital's rule the first time,
Right.
you plug it in again
Right.
and see if it works.
And if it gave you 0, 0 again, then you just.
Yep. You just apply it again. So if you got 0, 0 again here, you do it a second time. And if
Do it till you run out of.
Yep, you do it until you can't do it anymore. So eventually it's going to run out. Yes.
I'm probably not thinking right now, but couldn't just, what do we say, 6x over 4 just be simplified to 3x over 2 without needing to,
Oh yeah, you could have.
without
Go
doing the
ahead.
second derivative, right?
Oh yeah, you could have just canceled out that, but it was kind of to show that you can apply it more than once. Yeah, but if you did cancel out the x's, it would have done the same thing.
Right, okay,
Any other questions on this one? All right, so let's. Hmm?
I don't know if you'll do an example of this already.
Mhm.
But what if we have, like, instead of it being like 6x, it end up being like 6x squared, but at the numerator is 4x. So then when you did the derivative again, you'd still have a variable on top,
Mm-hmm.
but no variable on the bottom, and it would be to infinity. So what would?
Oh, then
Match though, would it?
Yep, then your limit would just be infinity. So really, you wouldn't have a limit.
Okay.
Yep.
So there would, for something like that,
Mm-hmm.
the answer to the question would be there is no limit.
Yep, limit doesn't exist.
But it doesn't.
Because the limit is just how high it's going to go. So if it's going to infinity, then
Right.
there's no limit to it.
But it's not indeterminate.
Yeah, it wouldn't be
Right,
indeterminate
if it doesn't
form
meet
at
the
that point.
indeterminate form.
Oh yeah, if it's not indeterminate, then that means you couldn't apply L'Hopital's rule to it again.
So you stop there.
Yep, so you stop there.
Okay.
So
Yep.
there's a difference between, there's a difference between indeterminate,
Mhm.
which is your infinity over infinity,
Mhm.
and then doesn't exist, which is either infinity or divided by zero, I think it is, right?
Yep,
Okay.
that's it. So it has to be in that infinity over infinity or 0 over 0. It has to be in that form. All right, so let's say, for example, here, and we'll probably have to wait till next time for Newton's method, so we can probably make it here. Okay, so let's say if we have, actually, let me find the limit as x approaches infinity of e to the negative x times square root of x. All right, so for this one, the limit as x approaches infinity, this you can rewrite it as 1 over e to the x times square root of x. So here, as x gets bigger and bigger and bigger, you have 1 over a really, really, really big number.
Wait, is that 1 over e of x times
Yep.
square root of x? So is that on the bottom? Or is
Yep, and actually we actually just made this e to the negative x equals 1 over e to the x.
X is a power.
No, I'm saying the square root of x. Is that like underneath the?
Oh, I see what you're
Yeah.
saying. Nope, that's actually just
Because
multiplied.
that's why I was like,
Yeah, so we're just multiplying those two.
just making sure.
Okay. So if you plug this in here, as x gets bigger here, that's get closer and closer to 0. So you really end up with 0 times the square root of a really big number is still a really big number. So that just becomes infinity. Okay. So that's not an indeterminate form. So we wouldn't be able to use L'Hopital's rule here.
But wouldn't that just be 0 anyway? Because 0 times anything is 0.
Oh yeah, for this one it would be. But you have some of them that they wouldn't be. So.
Okay.
When you say e to the x, is that a variable or is that natural log?
Natural.
That's just the number e, which is 2.7189,
So how
blah,
would
blah,
it
blah.
equal 0 then?
Oh, because you have a number, let's say if you have 1 and x gets bigger and bigger and bigger. So if you plug it in, let's say you plug in 0, you have e to the 0, which is 1. So if you plug in 5, you have, well, let's say 5,000. Then you have 1 over e to the 5,000, which is really, really, really small.
Oh.
Then let's say if you plug, so as your x is getting bigger and bigger and bigger, that number is getting closer and closer and closer to 0.
Pretty much the limit
Yeah.
of that would be 0.
Yep, the limit of it is just
It's not
0.
literally the number being 0. It's
Yeah, just the limit. And that's the one thing about limits is that it's not that actual, it'll never actually be 0, but it'll just keep getting closer and closer. Okay, so that one's not indeterminate. Like I say, you could just say 0, but technically, just to show how you can kind of manipulate the equation, so you have, let's say, square root of x over e to the x. Okay, and that one little change makes a big difference. Because if you plug in infinity, the square root of a really big number is just still a really big number. And e to the power of a really big number now becomes just a really big number. It's no longer divided by 1. I mean, divides 1, so it's no longer having a limit of 0.
So is it safe to assume if our question is presented to us in anything other than a fraction?
Pretty much. Yep, if it's, and sometimes even if it's in a fraction, you have to kind of mess around with it a
So
little
it's
bit.
not cut and dry then?
Yep, so if you plug it in and it's
It
not
looks like
infinity
if
over
it's just in a
infinity.
good fraction, then it's gonna come out, you can use it no matter what.
Not always. And I'll give you an example of when it won't come out. Okay, so here we can actually apply L'Hopital's rule. So we have the limit as x approaches infinity. Uh-oh, clean that up some. Of the derivative square root of x over the derivative of e to the x. Uh-oh. So the derivative of square root of x, and actually I'll make that x to the 1/2 power. So it'll be a little easier to derive. Yep, so you have 1/2 x to the negative 1/2. Derivative of e to the x, remember that's just e to the x as x approaches infinity. So that square root of x becomes square root of x down here. So really that's just the limit of 1 over 2 square root of x e to the x. So as any of those x's gets bigger and bigger and bigger, this just gets closer and closer to 0. So that ends up being 0. Which we kind of knew from the beginning, but that's how you would use L'Hopital's rule for it.
Because we said, wait, why would it be indeterminate? Oh, because we said 0 multiplied by infinity.
Yeah.
So it's just going to be 0.
Technically, even though 0 times anything is 0, infinity is not a number. So that's why we can't have 0 times a value that's not really a number.
Okay.
So infinity just represents a continuously growing number.
Yeah, so that as the number gets larger and larger, it just gets closer and closer to 0. So
Yeah.
we can put 0 because it's the limit. It's
Exactly. Yep. It'll never actually equal 0, but its limit is 0. All right. Any other questions on this one? Yes.
Why was the derivative of e to the power of x e to the power of x? I feel like we went over that a while back.
Yep. You have the limit of, I mean, not the limit, derivative of e to the x is actually still e to the x, and the derivative of e to the g of x is e to the g of x times g prime of x. I want to say I think it was the class or two before the last test when we proved it.
Yeah.
Yeah, so we actually did do the proof. Yeah. All right, so, quick note. This is probably one of the most important. If you have 0 times infinity, infinity times infinity,